All right, let me quickly check with you what you see on the screen. Just type in the chat box so that I know you're seeing the right screen. Okay, chapter 16. Fantastic. That's what I wanted you to see. Thank you very much. So we are going to take about this SPC today, and then we will go into team collaboration and control checklist. Okay, so I want all of you to type SPC in the chat box, which is statistical process control. It consists of three components. One is statistical, the second is process, the third is control. So the process may not be under control. How many of you agree with me? The process may be under control, may not be under control. But then you cannot blindly say whether it is under control or not under control. Statistically, whether it is under control or not. How do you determine statistically whether it is under control or not? And that's what we are going to talk about today, which is the SPC charts, which is data-driven quality method that is used to monitor and control the process to ensure consistent performance and minimal variations. Okay, good. Now, if you see the entire DMAC methodology, define, measure, analyze, improve, and control. Those who are here for the first time, type DMAIC in the chat box. You must and should record this. Define, measure, analyze, improve, and control. And we have gone through all the tools here. In define, we have gone through a set of tools. In measure, we have gone through a set of tools. In analyze, we have gone through a set of tools. In improve, we have gone through a set of tools. And in control, we have gone through a set of tools. And today, we are into this SPC, which is statistical process control. Okay, good. Now, control charts. In this, you see two words here, upper control limit, average, and below you will find the lower control limit, which means that there must be some borderline in which you should operate your process. How many of you know driving? Just type me in the chat box. How many of you know driving? All of you know driving, right? In the driving, assume that it's a one-way road. Assume that it's a one-way highway. Now, the center line is a dotted line. On the right side, there is a white line. On the left side, there is a white line. How many of you can relate to what I'm saying? Type I, C, or I can relate in the chat box. Now, when you're driving the car, where would you drive? Would you drive towards the left white line or the right white line or the center line? Type CL in the chat box to drive towards center line. I'm talking about this is a one-way road, highway. There is no other traffic. You are driving alone. You are the only person who is driving. Assuming that you are doing the racing. Okay, you are doing the racing. It is your separate lane. Where would you drive? Okay, preferably center line. Suppose if you want to drive in the center line, can you exactly drive in the center line or would you wobble left and right? Can you drive exactly in the center? No. Why can't you drive exactly in the center? I would want to know something in the chat box. What are the reasons why it would wobble? It is plain road. There is no traffic. It's a separate racing track. It's a straight racing track. Due to manual interventions, due to road conditions, due to the air in the tire, maybe due to your steering adjustment, and so on and so forth. So there are a lot of reasons, there are a lot of causes which will make you shift apart from the center line. So this is what I wanted to communicate to you. Similarly, when you want to produce a product of say 10 grams in weight, plus or minus 0.5 grams, you cannot produce exactly 10.00 grams. It will be plus or minus some 0.2 or 0.3 grams because of the machine conditions, because of the material conditions, because of the manpower conditions, because of the measurement conditions, and because of other environmental factors. If this is clear on a scale of 1 to 10, please give me a 9 or 10. There will be a variation. Now, Dr. Edward Deming and Dr. Walter Sheward, okay, popularized the quality movement, and Sheward charts. Dr. Walter Sheward actually extensively used this control charts. Okay, now I'm not going to read all these things, but uses statistical tools to analyze process variations, aim to maintain process stability, improve quality, involves data collection, and distinguishes between common cause and special cause. All of you type CCV, SCV, common cause variation, special cause variation. Please type these two words because the strategy for common cause variation is different from strategies for special cause variation. Special cause variation means, suppose suddenly something comes on the road, you turn to the left, that is a special cause. But naturally, if it wobbles left and right, it is a common cause. Suddenly, you feel asleep and you shift towards the left or right, that is called a special cause. Whereas naturally, even when you're so steady, still you're going left and right, that is called as a common cause. Okay, so common cause, there are many common causes, but each cause will have a less impact on the variation. Whereas special cause means there is a few, one or two special cause, but it will have a huge impact. For example, if you're feeling asleep while driving, suddenly the vehicle shift to left, that's a huge impact. So common cause variation and special cause variation is, special cause is caused by external unexpected factors like machine breakdown, operator error. This needs investigation and corrective action, whereas common cause is inherent in the process. Okay, minor temperature fluctuations in manufacturing. It is stable and predictable within control limit. Common cause is stable and predictable within control limits. This is the takeaway from this slide. Okay, stability does not mean capability. Please write it down. Stability does not mean capability. If common causes are produced, the process will be stable. Okay. So if you see Lean in Six Sigma, Lean focuses on waste reduction. Six Sigma focuses on reducing the variation. Okay, SPC plays a critical role by a structured way of measuring and controlling the variation. Okay, in different phases, we use this statistical process control. In measure phase, you see the baseline performance. In analyze phase, you study the process variation, identify root causes. In improve phase, if you see, you validate the improvements through statistical analysis, and in control phase, you make sure that the process is stable and improvements are sustained. Okay, so far, if you found it interesting, useful, valuable, fantastic, awesome, put it in the chat box. Okay, let me proceed through the session today. Now, I'll give you a feel of, most of these graphs are done by softwares, and particularly I use software called Minitab. Thank you. So if you see here, there is a red line on the top and the bottom. There is a green line in the middle. There is a blue line in the center. And so the red line on the top is called as the upper control limit. The red line on the bottom is called lower control limit. And the green line in the center is called as data average. And the blue line is actually the data points that are connected by the line. Okay, so this is, so all of you type UCL and LCL. UCL is the upper control limit and LCL is the lower control limit. And also you can write CL, which is center line, and average. Center line and average always may not be the same line. Okay, the average might be shifting from the center line many a times. Our objective is to make sure that average is overlapping on the center line, but in most of the cases, since the process drifts and shifts, it may not be on the center line. All right. The data points which is there on the control charts can be put in the form of a histogram also, like this. If you see here, histogram which is on 90-degree tilted, right? And if you see, there are 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth, many data points here. But if you draw a line here, and these lines are forming the histograms, okay? See, for example, okay, if you see here, all these data points are are coming towards the center. So many data points here. If you see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 13 data points here, whereas there is one data point here, and probably there is one data point here. And there are a few data points, which is, if you see here, all these data points here correspond to this area. Okay, so if that is clear, type super clear SC in the chat box. So this control chart is also, you can juxtapose as the histogram. Super clear. And that is why, if you see the upper control limit here and the lower control limit here, and there's a lot of data points which is mapped as a histogram. So the difference between the last one and this one is here it can also be the subgroups. Okay, subgroups means how many data points are between 7.5 grams to 8.5 grams. How many data points are between 8.5 grams to 9.5 grams. How many data points are between 9.5 to 10.5 to 11.5 to 12.5. And that is how this is written. The earlier was a direct single point, and here is a grouped point. That's only difference, and that is why we come to two types of control chart called individual chart and X bar chart. Okay, X bar means average chart and individual chart. Okay, please write in your notes average chart. But later on, this individual charts, I will say IMR chart, which is individual moving range chart. X bar chart, I will call it as X bar R chart. Okay, so this is a little bit of depth of a subject. So not many people will stay back till the end if I start sharing the details of this. Okay, so individual moving chart will always be like a time order data. In the time sequence, you collect the data like a temperature, pressure, or whatever it is, and then keep plotting from time to time, and then you evolve the upper control limit and lower control limit. And how is this upper control limit, lower control limit calculated? For each type of data points, whether it is continuous or attribute, whether it is grouped or individual, there is a formula for that. I will share with you all the formulas of that. Okay. And so these are the components. As I told you, this is a mean, upper control limit. Now I have introduced the formula. Mean plus 3 standard deviation, mean minus 3 standard deviation. Mean and average both are same, by the way. Okay, if somebody asks you what is the difference between mean and average, don't think it is different. Both are same. Okay, plus or minus 3 standard deviations. Okay, all of you type M plus or minus 3 SD. Okay, 3 standard deviations. So upper control limit is plus 3 standard deviations and lower control limit is minus 3 standard deviation. Excellent. This is for the individual moving range chart. Okay. Okay, no problem. If somebody is not following it, please go through this recording and you will understand it. Okay. Sometimes, these are all statistical concepts. If you don't focus, you might get lost. That's okay. Just keep focusing. Now, if you see here, there is an average because the data point has an average, and there is also a standard deviation for the data point, and plus 3 standard deviation you will draw an upper control limit, minus 3 standard deviation you will saw lower control limit. But if you see here, this is going above the upper control limit. Whenever it goes above the upper control limit, it means special cause exists. Okay, special cause exists. That's a symptom of a special cause. When it is above or below the control limits, it means it is a symbol for special cause. If this is clear on a scale of 1 to 10, please give me a 9 or 10 if it is super clear. And this is the way by which you can know that there is a special cause that is exist. All right, thank you very much for those who are paying very good attention here. Okay, and that's why if you see here in this place, there is an upper control limit, there is a lower control limit. If you see on the left side portion, so far the process has been stable, but suddenly something has happened to the machine, or suddenly something has happened to the process, and hence it has shifted beyond the control limit, and hence this is assignable cost, special cost, which means that this has to be isolated and treated separately. This has to be isolated and treated separately. Okay, this is one coffee chain sales by year. If you see here, there is a special cost that the coffee sale has increased. Okay, maybe it's a hot time or maybe it's a season time or whatever it is. But then the average sales after the improvement, it has increased from somewhere around 33.5K to close to 35K. Okay, and also the variation is decreased. So this is how we show the improvements. Okay, this is a 2012 year, this is a 2013 year, before and after if you show. The point that I'm trying to communicate here is control charts, you can share visually the improvements before and after, you can share visually the trends, you can share visually the shift and drift. All of you type shift and drift in the chat box. Shift and drift. So it can tell you what actions you should take when things go shift and drift. These are the two important words that you should learn. Okay, so SPC is a data-driven quality control method. And depending upon the type of data, okay, we should use different charts. This chart is something that I'll give it to you towards the end, okay? This flow chart is something that I'll give it to you. It is also an output from the mini tab, okay? There is a continuous data, there is an attribute data. What is continuous data? What is attribute data? We have explained in data types. And even continuous data can be in subgroups. If it is not in subgroups, it's an individual means you use individual moving range chart. If it is in subgroup, whether it is 8 subgroup or greater than 8 subgroups, depending upon that you use X bar R chart or X bar S chart. If it is an attribute which is defects, okay, or defects per unit, defective items and defects per unit, depending upon that you use P chart or U chart. Now, the point here is, boss, this looks like a big headache for me. How do I remember this? Don't worry about this. Do not remember this. All you should know is there are two types of data, continuous data, attribute data. And in continuous data, if you are going to monitor the individual, then you use an IMR chart or otherwise X bar or X bar S chart. If it is an attribute data, either P chart or U chart. Finished, period. Okay, and everything software will help you. Okay, all of you type simple in the chat box. Don't get complicated with this. Okay, all of you type, please type simple in the chat box. I want to inspire you to really feel that this is not a rocket science. Everything's, once you enter the data, the software will plot all the graphs for you. Okay, so don't worry about that. All that you should know is choose which type of chart that you should. Okay, great. Thank you very much. Okay. Which chart to choose? I'll give you this. Okay. All you need is a U chart, P chart, C chart, NP chart, I chart, IMR chart, and X bar R chart. Okay. So no complications. There is a flow chart. In fact, depending upon what you choose, software will automatically plot that type of a control chart. So this is not a rocket science at all. So I'm not going to read whatever is written here. The point here is I wanted to bring to your attention that there is a red spike that is here in the top. The red spike indicates that there is a special cost. Okay. All that I know is that what is the knob to adjust? What is that you should do when this goes out of control like this? Okay. So Dr. Donald Wheeler said, failure to use control charts to analyze is one of the best ways known to mankind to increase cost and waste efforts and lower morale. Okay, which means that please use these control charts to really monitor. You have to monitor your BP, you need to monitor your sugar levels, you need to monitor your vitals. You can afford not to do for your health, but not for the health of the output product, because you are giving that product day in and day out to your customer. Okay. So if you want to separate the special cause from the common cause, it's something like this. Okay, if you see the data point like this is the upper control and lower control limits. And you see this is a mean and upper control limit, lower control limit. And this is the region of special cause variation. Okay, and center is region of natural causes of variation. Okay, the natural cause is also called common cause of variation. So it will clearly tell you whether the special causes are present or not and what actions to take. So there are some rules that we need to follow. Okay, first let me explain those rules. 3 sigmas from the center line outside the control limit. The first rule is if it is above the upper control limit or lower control limit, that means it's a special cause. Apart from that, 9 consecutive points on the same side of the center line. You see 1, 2, 3, 4, 5, 6, 7, 8, 9. That is also a special cause. And third one is interesting. 6 consecutive points increasing or decreasing. If you see here 1, 2, 3, 4, 5, 6, 6 points are increasing or 6 points decreasing. That is also an indication of a special cause. Okay. 14 consecutive points alternating up and down. That is also an indication of special cause because some operator is tweaking the data every now and then. He is trying to bring it within the control limits so that he doesn't get fired by the production manager. How many of you can relate to this type ICR? I can relate in the chat box. People keep tweaking, right? It goes up, again tweak it. It goes down, then again tweak it. Tweak it, tweak it, tweak it. Good. Thank you very much. Now, so we said variable data, attribute data. And I've already mentioned this. I will share this presentation with you. There are 3 types of charts we have seen. Individual moving range chart if the subgroup size is 1. Okay. And depending upon the variable sample size or constant sample size, okay, you choose the type of charts that I've seen. I have already explained this on the flow diagram. This I'm just explaining through a table. Okay. So attribute data, you have all these type of charts. P chart, U chart. These are the 2 main charts. Okay, P chart and U chart. Here, X bar R chart and IMR chart. If you learn these 4 charts, that's more than enough. This is widely used. 80 to 90% of the time, either IMR chart, X bar R chart in variables, and P chart or U chart is used. No other chart is quite widely. So in the IMR chart, if you see here, in the top, if you see individual plots are plotted, individual values are plotted. In the bottom, the ranges are plotted. What does it mean? The first 2 data points, if you take the difference, that is called as a range. Moving range. All of you type MR in the chat box. Individual and moving range. IMR. IMR. Individual I-MR. Individual moving range. Let me explain to you this. Okay, this is the moving range. Okay, this is the moving range here. The individual points are plotted on the top of the chart here. Okay, so this is the special cause. These are the 2, it is going outside the control limits and something has happened here. We know that. And if you see here, the individual data points, the difference is actually 2.2, which is plotted here. The first 2 points, which is the difference, is plotted here. And this is called as a moving range. If this IMR chart construction is clear, give me a 9 or 10 if it is super, super clear. Fantastic. Okay. Now, I'll also show the data. There are some formulas to calculate in this. I will share with you sort of formulas I used in calculation. I'm not going to explain those formulas. Okay. It is boring to explain all those formulas. But formulas, the softwares automatically take the formulas and calculate. So all I want to understand is the construction of an IMR chart. That's all. See, for example, the pull test data. Okay, 2.38, 2.06. What is the difference between 2.38 and 2.06 is 0.32. Okay, 0.32 is the difference. Similarly, the difference between these 2 is 0.3. Okay, and so on and so forth. So this is the individual value. Let's see how this is plotted. Okay, let's see how this is plotted. So if you see here, the first two differences put here 0.32. The difference between the second data point and third data point is 0.4, and so on and so forth. And there is an average for the moving ranges. Okay, and also there is an average for the entire data set. The average for the entire data set is actually given here, and also the average for the moving ranges given here. Okay, if this is clear, type super clear SC in the chat box. All right, thank you very much. So are there any special causes present? You can always check this out. If it goes out of this somewhere, if it goes out of control limit, then special causes are present. And so I have seen this, I'm not going to explain this right side, but then you can always show in the IMR chart before and after. Okay, and if you see the IMR chart here, this is an output from a software which is Minitab, and it will quickly show you. If you see in the moving range, this red color points indicate that things are going out of control here. Okay, so the question here is, let me ask some question here. When should you use IMR chart instead of X bar R chart? I have not animated this. Okay, sorry about this. Just give me one moment. Okay, I have to change the order of the animation. Sorry about this. Correct answer should come on the edge of it. Let me see. Okay, the others seem to be right. Okay. All right, so let me come back here. When the sample size is greater than 10, when the data collected is in subgroups, when only one measurement is available for the period. Okay, let's see what is the right answer. Okay, when only one measurement is available per time period. Okay, fantastic. Thank you very much. Question is, what is the primary purpose of a moving range chart in the IMR chart? What is the primary purpose of moving range chart in the IMR chart? To monitor the mean of the process, to track the variation between the consecutive parts, okay, consecutive individual points, to calculate the median of the process or compare the process variation over a period of time. Let's see what are the answers that people give. To track the variation between consecutive individual points. Okay, all right. So we will get into the X bar R chart probably in the upcoming session. If you found today's session interesting, useful, valuable, fantastic, awesome, put it in the chat box.